Okay, the thing with images is okay, by default they're all set at a certain resolution in the current age. There used to be a certain point of time when images were taken on films. When the images were taken on films, the only real limiting factor was how much we were able to differentiate each of those molecules in the film. So based on that, the clarity or the quality of the photo image taken was determined. When we moved into the digital space, that's when these super resolution techniques that we're going to talk about today came into play. Let me start with the definition of resolution first. Okay, most of us would have the notion that when we say the term resolution, it's gonna be some x pixels by y pixels. That is not really the case or the actual definition of resolution. I hope people can actually read this, but let me just repeat anyway. It is effectively the shortest distance between two points that you can definitely or determinately say that they are separate. That is what is actually meant by resolution. And coming to image super resolution, we can trace it back to about 1940 or 1950s when it was really taking a lot of interest from researchers as well as particularly the defense sector. I mean, US Air Force had specific test patterns and specific testing criterias to determine what, or rather, how much a system is effective enough. That is when it really took people really took interest in image super resolution. So again, coming back to the 1950s, the people were mostly trying to work with optical domain because they were still limited to film. When we are working with film, our limiting factors are first the optical clarity of the lens, the optical clarity of the atmosphere, effectively how clear the atmosphere is, and then all the subsequent processing elements, you could say, all the way from the lens focuses the image onto a film or the imaging medium, and that imaging medium is then like stored as like archived, and that archival process also matters because over time film degrades and thus the image clarity also degrades. So this whole chain of events need to be perfect to get good clarity. Okay.
Tamim,
Yes.
it is not visible anything. Your presentation is not visible. And also you are copying and pasting the password, everything is visible in live.
Are the students able to see the screen? The students are replying that they are able to see the screen, sir.
Students are here. Raghav. Om.
It's visible, sir.
Sir, it's visible. You
Okay.
please spin the screen.
Okay, okay. Visible only, no problem.
Okay. The screen is visible as well as the slides, or am I visible?
Right now you are visible.
Slides are visible. Fine. That is what I need. Yeah. Okay. In the optical domain, when we work, when people were working with the optical domain, what was happening is,
Tamim,
yes, sir.
நீ உன்னோட ஸ்கிரீன்ல பின் பண்ணிடு. அந்த ஒரு ஸ்கிரீன் மாதிரி இருக்குல்ல பின். அதை பண்ணிடு, இல்லைன்னா யாராவது ஒருத்தருக்கு ப்ரெசென்ட் பண்ணிட்டே இருப்பாங்க.
ஓகே,
பின் பண்ணிடு ஸ்க்ரீனை. அந்த ஒரு பெல் மாதிரி ஒன்று வருது இல்லை,
யா,
அதை பின் பண்ணிடு. ஓகே.
இஸ் இட் ஃபைன் நோ? Okay, sir. Yeah. Just hold on a minute. Sorry. When people were working in the optical domain, they were not really trying to just get a better quality image, but rather they were trying to gain more information from it. Okay, and that information can be inferred in terms of details that we might not necessarily understand directly. Hello.
Somebody is asking some questions.
Yeah, okay. I'm seeing it's visible. I'm not seeing any questions in the chat. Does anyone have a question? Okay, since no one has posted anything, let me continue again. Okay, eventually we moved to geometric techniques or image processing when we moved from the analog domain to total digital domain. Okay, and yeah. Okay, this is effectively what it was initially tried upon. What happens is when you shine light through a microscope through the slide, the image is usually seen as such as A, B, or how you can see in A, B, or C. What happens is when you are able to shine the light through a structured element such as a diffraction grating and do the necessary optical corrections, you are able to get a much clearer image such as in D. Okay, this let people infer structures or the process details much better than they were able to infer earlier. Okay, let's come into our actual point of interest today. We are going to work with geometric or image processing super resolution. The most simple method would be single image interpolation. I hope some of you have some experience with OpenCV. In that case, you would have most likely used a cv2.resize function. That resize function effectively what it does is it takes 2 points in an image, and once you expand the image, it finds the mean of those 2 pixels to replace the pixels that are not available. Okay, and this method is not exactly super resolution because it is not doing anything but creating a mean of the pixels. And then we go into multi-exposure super resolution. This is more of a method that was used to get a better quality image rather than a higher resolution image. That was the primary focus of multi-exposure super resolution. And then comes single frame deblurring. This is okay, I guess this can be explained by any image where you know a spherical aberration to be present from the lens of the camera, most likely. Those are camera intrinsic properties that once you measure how it's affecting, you can always revert back. That is the kind of errors or fixes that can be done in single frame deblurring. And subpixel image localization, this is more of a microscopy technique, rather only in very small how do I put it, very small resolutions you would actually be able to use this. In a normal scenario, this wouldn't be any useful, or rather, the data what we infer from it won't be useful. And we have statistical methods and deep learning based methods. So statistical methods and deep learning methods are sort of related, but deep learning is way more complex, you could say. That, I guess, is the apt term. Okay, interpolation, I've already given an overall view of what would be done, and it's just pure mathematical techniques. There's nothing statistical. I mean, there's nothing complex about it. It would be a
Tamim,
nearest
Tamim,
neighbor, bilinear or cubic most of the time, and there are more complex interpolation methods, but most of us we stick to nearest neighbor, bilinear, and cubic. Um, okay, we
Tamim,
will. Hello.
hello.
Yeah.
Tamim, actually, here presentation is not showing, but better you can put live session. Everybody will see.
Okay. A live session is already streaming, as far as I know.
Yeah, already is streaming. So all the participants at least go with the live session. So I will already posting the link and the live session. Again, I will post. So better you can see in the live session.
I'll share the live sessions video later, sir, to you.
Yeah, live session is better because here presentation is not coming. A lot of problem is there.
Yeah, we'll better do that. Yeah, fine, sir.
You
Okay.
can present your own screen itself. It is not required on my account also.
So like I just hope I can just continue with what is already there. Since I'm sharing my whole screen and input device, it should not be an issue.
Yeah, that is why I'm saying take 5 minutes. You log out this one. You can send leave streaming you given to me. Then I will share to all the students.
Okay, sir.
Okay. So take 5 minutes and then give your live streaming YouTube link. Then I will share to everybody.
The live streaming YouTube link already shared is valid.
Hmm.
Okay. Okay, people, let's continue with interpolation. Okay. We'll see the effects of what happens with each of them in like a demo Jupyter notebook that's been made for this. And now coming to multi-exposure super resolution. Okay, this is a method that requires successive images to be compared, and there will be subtle pixel differences in any successive exposures, irrespective of it's mounted on a tripod or any solid mounting mechanism. There are always going to be minor most smartphones are also following this method right now, and they use it in HDR almost always, but also in other cases such as like you could use night sight. Particularly night sight, it takes successive um, exposures, but a lot more of them than that would be required in a daytime, and combines them using a lot of complicated methods, but effectively multi-exposure super resolution. And you might ask a question of what happens when 100 megapixel cameras are coming up in smartphones. You don't really use those 100 megapixels. What happens is, like, they'll be combined together to do pixel subsampling, and 4 pixels, or sometimes in case 2 pixels, or any number of pixels can be combined to act like a single pixel. And the necessary conditions for multi-exposure super resolution: we need at least a subtle motion of the sensor. This will always be present in any fixed solutions included, and the required output resolution is within the intrinsic resolution capability of the sensor. This particular second statement is very important, because with respect to multi-exposure super resolution, you can't get extremely higher resolution that you expect, but rather it improves the quality of the image at the same resolution. Okay, this particular example or figure, you could say, is pretty much what multi-exposure super resolution it's supposed to be. What happens is, within each exposure, considering exposure 1 to be squares, exposure 2 to be circles, and exposure 3 to be triangles, what happens is, like, these are subtly different from each other. They're like slightly geometrically displaced, you could say. All of that can be combined to form an image that contains the information from the 3 exposures as shown below. Those 3 can be combined in any number of ways. That depends on the internal algorithm that is being used by the particular implementation of the super resolution algorithm. Okay, subpixel image localization. This is actually quite an interesting application of how image localization can be done. What happens is, like, but it requires that all the light sources or the light emitters in the viewport need to be point sources. They cannot be a beam. They have to be rays. Only when they are point sources, what happens is, like, okay, consider that you have 10 pixels, okay, and in 10 pixels, what happens is, like, each of the we call each of these light emitters as fluorophores. Each fluorophore is turned on and off for a very short amount of time, and their different fluorophores are illuminated at each instance of time, and a huge number of exposures is captured just until enough. The threshold depends on the particular application, but once enough fluorophores are captured, they can be reconstructed into an image like this. And the one particular okay, sorry, apologies, my internet connection must have slowed down, I don't know. What happens is, when a single particular point source is illuminated and you have 10 pixels arranged horizontally, the intensity of the light from the particular point source to each of them is going to be different, and using the difference or the deviation in the illumination per pixel, it can be reconstructed into a more finite location. Rather than saying that the point source is present only within a pixel, you can say within a pixel, within 1% of the area, that point source is present. This is this particular image that you are seeing on the screen is 0.5 micrometers is the crop size, but then the individual pixels that you can see are much smaller and are way beyond normal microscope's resolution power. So this particular technique of storm is being used as an approximation of electron microscopy. And okay, now coming to statistical method, and in statistical method there's again another implementation of interpolation super resolution. In this implementation, in this particular method, what happens is, like, you take a lot of low resolution observations and you also take them at different orientations also. That is also allowed. You are not limited by this only subpixel shift that was present in the previous interpolation in the previous method of combining multiple exposures. This particular method can be used and is used a lot by astrophotographers who have stars to align. Okay, a constellation. I hope everyone knows what a constellation is. Constellations are particular arrangements of stars that are not gonna change their geometry, and when those geometries can be aligned in an image over multiple frames, you can infer way more information, or rather you can stitch together so many frames that you can get a higher resolution frame as well as an interpolator, and it's deblurred and it's also going to be denoised because of the advantage of multiple frames being captured. But the pitfall of this method is that you need a huge number of pixels exposures, an extremely large number of exposures, and once you have a certain number of exposures, you need to do the image geometry registration. By image geometry, I mean the particular arrangement of the features within the image. In this particular case, I guess you can take the diamonds as one feature and triangles as an the diamonds, triangles and the circles are different features, different exposures, and the arrangement of each of them is the feature, and they can be aligned together over multiple frames. And this computational expense is what is holding back statistical method of interpolation SR to be not actually used in real time, but is more of a post-processing step. And coming to example based methods, these are the most robust method in the traditional space, and it also requires prior knowledge of the image space. By prior knowledge of the image space, I mean if you want to work on say shapes of houses, you need to have a huge number of houses already photographed and the geometry of them recorded and organized in a particular fashion. This is its biggest strength as well as pitfall. What happens is, like, you need to have a huge number of exposures and they need to be registered properly, and this can act in both directions. And yeah, computational heaviness or the computational expensiveness of the algorithm during the actual inference, or inference you could say, that is what is actually stopping example based methods, but it was being used until deep learning methods were bought up. It's a double-edged sword. Okay, the volume of prior knowledge. In this image, consider the four internal intersections to be x1, x2, x3 and x4. Okay, by x I mean low resolution patches, and by y I mean high resolution patches. Okay, and what happens is, like, you have a one-to-one mapping of low resolution patches to high resolution patches in this particular case, but the mapping of one-to-one or one-to-many or many-to-one depends on the particular registration that is being done. Effectively, what you do is, for any small patch you find, you replace it with a larger patch. When you replace with a larger patch, it's gonna create a couple of issues. One is gonna be the edges of each of the tiles. Each of the edge tiles are not necessarily gonna be coherent, so there will be an edge difference. Those if you can see in the LR patches here and LR and HR patches here, placing them right next to each other is gonna create a discontinuity in the image. So what people or researchers try to do there is a weighted addition, or they have many methods to resolve that. That is one issue. Next is what happens when you have low resolution patches during registration. During registration, you need the low resolution and high resolution to have a certain relationship in terms of scaling. If that scaling factor is too large, you won't have a proper registration to replace low resolution patches with high resolution patches. And next challenge is the modeling of the problem. Most researchers, what they do is they model the image registration and the estimation as a optimization problem. When you're modeling a problem as an optimization problem, you are placing a lot of constraints, and this constraints can cause overfitting at times because it is an optimization problem. And what happens to the model when it's outside of the registration conditions? The registration conditions may have been done for example, white-haired people, and when the same model is being applied for black-haired people, or you can even take a frizzy hair versus straight hair. A model registered for frizzy hair is not going to be able to perform on straight hair because of the total difference in the geometry of the features again. Okay, now we are coming to deep learning based super resolution. But before we see deep learning based super resolution, I like to run a couple of samples to show you what happens in each of the simple interpolation scaling methods. Okay, now let's see what linear interpolation does. What we do is we do a 4x downsampling and then upsampling, back 8x downsampling and 8x upsampling, and this is the amount of recovered details in linear interpolation. In linear interpolation, if you could observe the particular whiskers in particular, you will be able to see what we lose. And this is by far the most computationally least expensive method, but also not necessarily the best quality method. And coming to nearest neighbor interpolation is something is a method that tries to just place the closest matching pixel in the vicinity to that location, to the missing pixel. Just a minute, guys. nearest neighbor can preserve the information that is present in the image as such, but does not necessarily give you a better looking image. And bicubic is supposed to sorry, not bicubic, cubic is supposed to give the best best looking samples of all of them. It's supposed to maintain the most amount of information. And if you can okay, let me stack them side by side. Okay, this particular example that we are seeing in the with the dogs is actually the hardest kind of example that can be given to interpolation algorithms, particularly hair. Okay, now let's go back to the method. Yeah, in deep learning super resolution, we are gonna look at the 4 of these samples. When coming to deep learning, it's more of learning a template and apply using that template to regenerate pixels. And so far what happens was, it was all either mathematical calculation or it was using examples to replace low resolution patches with high resolution patches. But when you're using deep learning in super resolution, the models start to hallucinate. Please don't understand hallucinate in the traditional sense of it, but effectively what we mean by hallucinate is the models tend to think that there are these kind of that think that new pixels are available. That is how we use deep learning super resolution. And we are going to be reviewing the 4 methods here. And SRCNN and FSRCNN are extremely close related. FSRCNN is effectively a improvement of SRCNN. RDN is a different method, and Waifu 2x is a method that is a model that was trained on anime and then also fine-tuned for photos. This is one model that you guys can run in the browser on your own systems. Mobile browsers I wouldn't recommend. It's not gonna be all that easy to run. It takes a couple of minutes to run on a full desktop PC. Okay, the structure of SRCNN. We have a low resolution image and image as input and a high resolution image as an output. This lower resolution image that you can see in this figure is the same size. In this particular figure is the same size as the high resolution image because it has been upsampled using bilinear upsampling as the input for this. This particular model needs bilinear upsampling to be done and that output to be provided as the input to the model. And we have 9x9 filters. 9x9 filters are effectively very large filters that register large patterns within the image and create 64 feature maps. These 64 feature maps are effectively the representation of the whole image as to what is present. And that representation can then be used to recreate or reconstruct another representation that is useful for upsampling to a high resolution image. This non-linear mapping here is effectively a dense layer. You could assume it to be a dense layer, and that dense layer lets you form extremely complex connections between the low resolution feature maps and the high resolution feature maps. And another thing is, you need to run this block by block. Consider you have an image that is 27 cross 27, and you're running an input size of okay, let's go with 270 cross 270, and you have an input size of 27 cross 27. In this case, what you would have to do is you would have to run it 100 times in a raster fashion to get all the blocks upsampled, and then you have to post process it again to remove the edge blurring, edge artifacts, and each block is separately reconstructed and then combined. Okay, for you to understand what SRCNN and FSRCNN are, how they are different, I have a small example of RCNN versus fast RCNN. RCNN and fast RCNN are object detection models. What happens is, like in an input image, you're saying a huge number of proposals. Okay, saying that in this X, in this point 1 to point P1, P2, P3, P4 enclosing a rectangle, there is an object. We throw a huge number of proposals, and those proposals are each separately evaluated by a deep learning model, and that model output is fed into an SVM, and that SVM classifies if an object is present and what class of an object, what kind of an object. This is an extremely computationally intensive process, and people tended to not use it it was not usable in real time, even with a huge number of computational ability. And then came fast RCNN. What we do is we run a feature extractor on the whole image first, and those the extracted features are used to create the region of interest that has been proposed in the previous method. So effectively we are shuffling around the order of the operations, and this creates a huge boost in the performance of the models. And the same has been done with FSRCNN. The first, the top representation is the SRCNN. We extract the we extract the features and create a representation, and that is created a nonlinear mapping through a conv layer here, and then the higher and then the feature maps that are created from the nonlinear mapping, they are used to reconstruct the higher resolution image. This is this is the SRCNN method of doing. With FSRCNN, what happens is you have a feature extraction first, and then you do a shrinking. That is effectively you are doing a downsize of the feature maps. You're creating a higher level representation of the features compared to what the raw features we extracted, and then the mapping happens between the shrunken features and the features to be expanded, and this expanding is effectively a transpose convolution or a deconvolution, depending on how you would try to implement. And then that reconstructed features is passed through a deconvolution operation, and high resolution image is performed. And here you can see the performance of the models, the original versus the bicubic. And if you see in the bicubic interpolation, you can see a large number of artifacts, and coming to SRCNN, you can see a large improvement in the noise levels as well as the reduction in artifacts. And then we have an extended SRCNN, that is able to perform slightly better, though we are not able to see it visually in terms of the scores they are evaluated. And running through all of them, we go to FSRCNN towards the end. In terms of FSRCNN, you can see a clear and marked improvement in terms of how the visual samples are improved. Okay. Now we are going to GAN. Okay. The thing about GANs is it's not a straightforward training approach as with FSRCNN or other methods. In FSRCNN, in SRCNN and FSRCNN, what you can do is you can directly compare the original high resolution image and the output high resolution image, and the mean difference between them is considered to be the loss. In case of GANs, you cannot directly apply that approach. You would have to do a more of a zero sum game. In SRR, ResNet is one of the traditional methods, as in the previous methods that we've seen, FSRCNN, it's similar to that. And we have SRGAN, that is what we are trying to understand what it's capable of doing. And you can see the original image here. Before coming to, let's come back to this image after looking at the structure of an SRGAN. In SRGAN, what happens is, like, you have a generator and a discriminator. Generator is supposed to do exactly what the previous kind of networks are supposed to do. Get an input low resolution image and create a high resolution output image. And you can use residual blocks and skip connections. The function of residual blocks and skip connections I'll tell, but that's more of deep learning related rather than super resolution itself. And then you have the second part, which is the discriminator. The discriminator network, what it does is it takes pairwise samples. Okay, it is supposed to get a high resolution and a low resolution, and compare and say if it is able to find them to be the same or not. The discriminator is supposed to get better at finding out the differences between a original image and a super resolution upscaled image. These differences are continuously learned, and this discriminator learning causes another couple of challenges with SRGAN. We'll come to that later. But effectively what you need to do is you need to train two networks in this instead of one. But SRGANs can do a very good performance if they are trained right. And GANs also exhibit instability properties when the generator versus discriminator is not properly configured, or the training of them is not maintained in a stable fashion. How do I put it? To put it in simpler words, the discriminator needs to improve with the generator. They are separate trainings, but they need to improve together, else you're not gonna be able to achieve optimal results. If you can see the original versus downscale to bicubic, you are able to we are not able to make out a whole lot of features in the face, nor particularly in the background leaves. Okay, and when using an SRR ResNet, you are able to make out much more features, but then what happens is you are not getting defined features. Particularly if you can see the headband and the neck, the scarf around the neck, and then also the leaves on the ground, everything is a bit soft. SRResnet is not able to work as optimally as an SRGAN. With respect to SRGAN, if you can see, you're able to get very good sharpness of an image, but you should also observe the hands in particular. Yeah, this is what I meant by hallucinating images. When we are hallucinating images, it thinks that the network thinks that the fingers should be in this shape, but that is not the case. It is able to approximate, but it's not able to get a good interpolation of that. If you see in the flowers in the background, you'll be able to see a clearly marked difference between how an SR ResNet is able to interpolate versus an SR GAN is able to interpolate. In an SR ResNet, if you can see, it maintains the shape, but just is soft, it's blurred. In SRGAN, it is giving very sharp images, but if you can see, the geometry of the flowers is messed up. This is what happens with SRGAN, and we'll also be facing a couple of more issues due to this kind of operation with SRGAN. You can also see the geometry of the jewels that are hanging from the headband. Okay, now let's go to in-browser image super resolution. Let me choose an image. This is a 4 times subsampled image from 2048. This is actually a 16 times subsampled image from the original resolution of 2048. And we are choosing a photo and choose an image. Okay, you can set. This is one particular restriction in this model right now. The denoising feature is not actually applicable in the photo because it was trained on anime in the initial space. So we are not looking at anime right now. Let's run the photo mode, and this waifu2x.js, what that model, what it does is it decomposes the image into a number of blocks, and each block is separately upscaled, and then the images are stitched together. Like in this case, it has broken down the image into 25 blocks. So effectively, a block size of about 10 pixels cross 10 pixels is what it's running. No, it's running on a block size of about 50 pixels. And while that is running, let's also run an RDN model. An RDN model, what it is it is a residual deep network. This particular library is directly available. IS image super resolution library is available in the pip repository. You can run it. The prerequisite is TensorFlow needs to be installed. Would prefer a GPU version because this is quite computationally intensive, and it'll automatically download the model so that you can use it as such. We have upscale by sample by a factor of 2, and let me go back to this. We'll see the results on this model and then compare the other model, compare with that model. And let me also open up the original so that you're able to see a difference of them rather than just these images. If you can see, you would be able to observe a lot more definition around the eyes and also around the nose. This is what we are trying to achieve by both waifu model as well as the RDN model. The other two models that we are talking about, SRCN and FSRCN, it is not possible to run it in the web browser here. So let me try to share the samples of them to you later. And that is the overall yeah. And with all of these models, what happens is there are the challenges of using image super resolution come up. There are ethical concerns in particular, because if you can observe the SRGAN model, what that happens is it is hallucinating features and not in the exact same geometry. And what happens is, like, when you're using GANs and hallucinating pixels or even deep learning models on the whole, you're gonna be hallucinating features or how a certain image or an object is supposed to look. And consider that you apply that for a face detection, face recognition system. When applying to a face recognition system, this is particularly detrimental, because you can end up identifying a person as a totally different person. And okay, also consider that we are correlating geographical presence of two people who are identified together. If they are in different cities or different states or in a totally different geographical locations, it can be somehow managed. Okay, but what happens when they are in the same geographical location? You might end up falsely incarcerating or putting mental stress on a person who has actually never been part of what you're trying to solve. This is one particular ethical concern. And also what happens is, if a GAN is sufficiently well trained, for example, you might have seen the style transfer GANs, and they can create photorealistic representations of drawings or cartoons even. In that case, if you are able to computationally manipulate the presence of another person into a scene, that carries a lot of ethical concern. And the whole way of training GANs, generator versus discriminator, is meant to defeat this very situation. It continuously keeps improving its discriminator, and the generator also keeps improving. So by human understanding, we are not able to separate the difference between a GAN generated image and an original image. The difference is becoming less and less and less. And then the robustness of deep learning method models comes into play. Deep learning models are always, again, similar to statistical methods, or rather example based methods, need to have a defined set, a defined sample set. Okay, when your sample set is not clearly defined, or your you're using the model in a non-sample set condition, the robustness or the accuracy of the model can not be validated in any meaningful way. And also another issue is you might train on a particular data set, and that particular data set might not be valid anymore. Again, it is an extension of the data set sample space coverage, but then this is a more common scenario that happens a lot in production. Even in industry, we are facing a lot of issues with this. We train a model and we ship it to the client, and the client tends to use it in a new scenario, or if there is a new environmental factor that is happening that was not part of the original dataset. These cases are putting a lot of stress on the industry as well. We are continuously trying to resolve them, and that's part of the challenges. And also there's another one challenge that is present with deep learning models. Even though they are computationally less expensive than example based models for the same size of the sample set, they are still computationally expensive. If you see the 256 cross 256 crop that I was running right now took in excess of a couple of minutes to upsample to 512 cross 512. That's just a 2x upsampling factor. When you need larger upscaling factors like 4x or maybe even 8x, it is extremely hard to provide the volume of computational resources that are needed by the models. And another concern that arises from high scaling factors. Only datasets are available for 2x and 4x upscaling effectively. 8x upscaling is not something that the research domain is exploring, nor the industry is really exploring. It's something that is more of a pipe dream right now. We'll eventually move to 8x, but not as of right now. And that is the end of the live stream. Any questions, please post it to my mail ID. I'll try to respond as soon as possible. I'll also try to ship a more usable form, or rather more portable form of the Jupyter notebook to you, so that you may use it, also with a requirement packages list, so that you can try it out, the RDN models. And I guess Wi-Fi you can try it out on the browser itself, but that has only an upscaling factor of 2. And also with the ISR library that we used here, it has a couple of more models, PSNR large, and it also has the ability to run a GAN based model. A GAN based model is extremely computationally intensive and cannot be run on a notebook GPU, most likely. You'd need a more powerful GPU. So just take note of that before you try to run it. Maybe you can try and collab. I hope, I think you'll be able to run that. Okay, thanks guys. That's the end of the stream.